Hello everybody and welcome to another AMC Learning Program lecture. My name is Hannah and today we are going to be talking about Fermat's little theorem and Euler's totient function and theorem and how these concepts will be useful in solving problems on the AME. So first let's talk about Fermat's little theorem, which we will state and then do a quick proof of. So the statement is as follows. So p is a positive integer prime, and then a is a positive integer such that a is not a multiple of p, or similarly, or like the same statement is that p does not divide a. Then we have two equivalent statements of this theorem. Both of them work, and depending on the presentation of the problem, using one or the other directly instead of deriving can save time. So we have that a to the p minus 1 power and 1 are equivalent in modulo p, or equivalently a to the p and a are equivalent in modulo p. Note that these are equivalent statements in that if you multiply the top one, both sides of the top one by a, then we get the bottom one. So now we're going to do a quick proof of this. So firstly, if sorry, I'm not really used to using this pen. But anyway, if a to the p and a are equivalent, then we have that a to the p minus a is equivalent to 0, and both of these statements are in modulo p. And then this gives us that p divides a to the p minus a by definition of modulo, since 0 in a mod means that this number is divisible by the mod. In this case, that this expression is divisible by p. So now we will proceed by induction. I hope that you know what induction is and the basics of how it works. So firstly, we have our base case, which is when a is 1. So note that here our induction is on a, which is a positive integer. So then if a is 1, then a to the p minus a is equal to 1 to the p minus 1, which is equal to 0. And then since p for any prime p obviously divides 0, then we are done with the base case. So the base case is true. Now we are going to do our inductive hypothesis. So for this one, it's when a is equal to k, where k is a positive integer, any positive integer, such that k is greater than 1. And the reason we do greater than 1 is because 1 was our base case, and we want to prove something more than 1. But note that obviously we could prove using induction actually for all values of k greater than 1, so this is a valid claim, and also this is just how induction would work in general. But anyway, our assumption is that p divides k to the p minus k. So now we're doing our inductive step. This means that it's the same as the above inductive step, which is we are looking at k plus 1 to the pth power minus k plus 1. Now we're going to do a cool manipulation here. So firstly, we have k plus 1 to the pth power minus k to the pth power minus 1. Now note that this cancels out the k to the pth power and the 1 terms of the expansion of this by the binomial theorem. So then this gives us p choose 1 times k to the p minus 1, summed all the way to p choose p minus 1 times k to the first power. Now since p is a prime, this means that p divides all of these binomial coefficients, including this one. And what that means is that this whole expression is divisible by p. Now, in order to get from this expression to our desired expression, which is this, we do this minus k to the p minus 1, and then plus k to the p, and then these two cancel out, and then minus k. So note that this is equal to k plus 1 to the p minus k plus 1. Now, what we have here is the following. So this part by our above proof, this is a multiple of p. And then this part by our inductive hypothesis is a multiple of p. And therefore this whole thing, so p divides this whole thing. And that means that our inductive step is true as well. And therefore by induction, we know that Fermat's little theorem is true. And we can use both statements of this theorem. Note that we proved this statement, but obviously we can also use this one depending on the context. So now we are going to do a quick sample problem using Fermat's little theorem. So the problem statement is as follows. If you want to try the problem on your own, then please pause the recording right now. So now note that these are all to the fifth power. And 5 is a prime, so we can use Fermat's little theorem here. We can use the a to the p is congruent to a in mod p. Since, well, all but one of these are relatively prime to, or actually we can assume that they are relatively prime to p. Actually, something I want to add about Fermat's little theorem on the previous slide is that if p does divide a, then this still holds true actually. Well, the a to the p minus 1 and 1 are equivalent, that doesn't hold true. But this still holds true even when a is divisible by p, because then both sides would just be 0. So anyway, here we have that 133 to the fifth power. This is congruent to 133. This is congruent to 0 by what we said above. So 133 is congruent to 3 actually. Then this is congruent to 84, which is 4, and then this is 27, which is 2, and then this is n. So then what we know is that n is congruent to 3 plus 4 plus 2, which is 9, which is 4 in mod 5. Now let's also use mod 3 to analyze this, because that's kind of a way to bound n using 2. It's kind of similar to the concept of Chinese remainder theorem, although we're not going to use that right now. So anyway, using modulo 3, what we get here is 133 is 1, so this is just 1, and then this is 2 to the fifth, and then these two are 0. So this is just 0. So then we have that n is a multiple of 3. Now, the rest of this problem is going to be kind of unrelated to Fermat's little theorem. We're just going to be using these two equations, and we're going to bound n. So firstly, note that since n to the fifth power is 133 to the fifth power plus some other positive integers, that means that n must be greater than 133. So then our solutions starting from there are 144, 174, 204, and so on. Now using other bounding, we get that 174 and onwards are too large, so these don't work anymore, and therefore our answer is 144. All right, so next, what we are going to talk about is Euler's totient function and theorem. So before we talk about the theorem, we are going to talk about the function. So for any positive integer n, which can be written as p1 to the e1 times p to the e2, p2 to the e2, all the way to pk to the ek, and note that here pi are all primes and ei are all positive integers, and note that they are positive because if they are 0, then we don't count them, since anything to the, or any positive integer to the 0th power is 0. I mean, it's 1. Sorry, it's 1, so it doesn't count as part of the product in n. So then the totient function of n is equal to n times 1 minus 1 over p1 all the way to 1 minus 1 over pk, which is stated here. Now, kind of a more intuitive understanding of this expression is that this can be thought of as counting kind of the number of positive integers less than or equal to n such that they do not share any positive integer divisors with n other than 1, or should I say they're relatively prime to n. So now the theorem is stated below, which is a to the phi of n, which is, this is red phi of n, by the way, the totient function. So a to the phi of n is congruent to 1 in modulo n. And then we note the very important condition, which is that a and n must be relatively prime, because otherwise this wouldn't work. Now, kind of something I want to note before we do a proof of this is that this is kind of a generalized form of what we looked at previously, the Fermat's little theorem, except here instead of n being a prime, n can be anything. And kind of a small thing I want to note is that if n is a prime, then let's say n is equal to p, right? Is equal to p1. Then the totient function of n is equal to n times 1 over this, which is equal to p1 times p1 minus 1 over p1, which is equal to p1 minus 1. And this is why we had the p minus 1 in the previous. So now let's do a quick proof of this. So let's think of this as follows. So first we have one set S, and we call its elements S1, S2, all the way to S phi of n. These are just, there are phi of n elements, and then each of these is distinct, and each of the s values represents one of the positive integers less than n that are relatively prime to n. So basically, these s values are the values that are counted by n's totient function. Now, let's think of another set, which is R. And then R is equal to A times S1, A times S2, all the way to A times S phi of n. Now let's note something. So A and n are relatively prime, and then each S value and n are relatively prime. So that means that each of these values is relatively prime to n. Now, since we counted all of those values already in set S, that means that each element in R corresponds to one element in S. So obviously it wouldn't be in the same order and it wouldn't be the same value, but they would be equivalent in modulo n. And so what we have is that these values are the same, in fact. So some S value corresponds to A times S1, and then this corresponds to another value here, and so on. So now, since these are the same, we can say that S1 times S2 times S phi of n, this is equivalent to, note that this is not necessarily equal to, equivalent to this. And then this, we can factor out the A, this is equal to, which is equal to A to the phi of n times S1 all the way to S phi of n. Now, since each S value is relatively prime to n, we can cancel out this part, this whole part. So this part just becomes 1, and then this part is canceled. So then, as desired, these two are equivalent. And note that our arithmetic here is done in modulo n. So we have our desired result, and thus we have proven Euler's Totient theorem. So now we are going to do another example, and this example relates to Euler's Totient theorem. So now, first, we note that the totient function of 49, and the reason we're using 49 is because here n is 49, since we want the remainder upon dividing by 49. So the totient function of 49 is equal to 49 times 1 minus 1 over 7, since 7 is the only prime factor. So this is equal to 6/7 of 49, which is 42. So now by our theorem, by Euler's Totient theorem, we have that for all a relatively prime to 49, a to the 42nd power is equivalent to 1 in modulo 49. And we note that GCD a and 49 is 1. Now, since the GCD of 6 and 8 with 49 are both 1, we can use this. So then A83 is equal to 6 to the 83 plus 8 to the 83, which is equal to 6 to the 42 times 2 minus 1 plus 8 to the 42 times 2 minus 1. And now since the 42, that would just be 1, so this part cancels out, and we are left with, this is equivalent to 6 to the negative 1 plus 8 to the negative 1. Now we're kind of finding the inverses of 6 and 8 in modulo 49. Obviously, we could just do this manually, but we can also do the following. So it's kind of similar to how arithmetic would work normally. So we can write it as common denominator, 8 plus 6 over 48. And then since 48 is equivalent to negative 1 in modulo 49, this is equivalent to negative 1, 14 over negative 1, which is negative 14, which is equivalent to 35. This is mod 49. And note that 35 would thus be our answer. So now here I have listed a few additional practice problems that you could try, and these would all use either Fermat's little theorem or Euler's Totient theorem or a combination of these. And note that these, just like the sample problems, obviously they wouldn't just use those theorems. You could also, or you would also have to use other concepts, other techniques, but these problems all relate to the concepts that we went over. And if you're like in the ALP Discord server or something, then you could ask me for the solution if you wanted. And then this is just a restatement of our two important theorems, and then that is it for this lecture. Thank you for watching, and I hope that you learned a lot.